I need to close that. Okay, everybody. Our speaker tonight is Alex McConahay. I've known him for, I don't know, 25, 30, I guess probably more like 30.
Junior high.
Yeah, since we were in junior high school. Anyway, he's a big mover and shaker in amateur astronomy. He's mainly involved in RAS. He used to be heavily involved in RTMC, which was a great event. I wish we were still having it. Anyway, and he does a lot of astro imaging himself from his observatory out in Landers. And so he's going to tell us something about astro imaging.
Hi, everybody. I've been involved in astro imaging a long time. I've also been involved in regular visual observing for quite some time. So I've had my thumbs in both ends of the hobby. I hear you're coming out to GMARS in a couple of weeks. I want all you guys, particularly in the back row, to come on out because that'll be fun. All this stuff that we're just talking about, that's not nearly as much fun as looking through the telescopes. So if you can come on out there, come on. Particularly be there by Saturday, an hour or two before sunset, so that you can find the place easily and stuff like that, and enjoy the barbecue, because there's a barbecue out there. Bring some, potluck thing if you want to, but mostly just be there and you can look at all the telescopes, okay? And it'll be a lot of fun. So I hope you're there, and I hope you're enjoying it. I'm part of the Astro Imaging channel, which is a group of people that put on a seminar every Sunday night at 6:30 California time, and we invite a astro imager of some kind or another, or a manufacturer, or a producer, or a scientist or something. Come on out and tell us about some aspect of astro imaging. And they talk for maybe 45 minutes. It's usually a little longer because they get to talking and you can't stop them. So at any rate, all of that stuff is broadcast over YouTube. So we'll have 70 or 80 people, maybe as many as 150, watching this guy or this woman, sometimes if we're lucky, tell us about astro imaging, some part of astro imaging. So, sometimes it's pretty geeky. Most of the time it's pretty informative, particularly if you're into the hobby of astro imaging. All of the shows are recorded and put out on YouTube. During the next week or so, we'll have anywhere from 400 to 500 people who tune in and watch the show. So please, if you're interested in astro imaging, hook up with us on the Astro Imaging channel, either live or come back and watch it on YouTube afterwards, because they're all recorded onto YouTube. But I get asked a lot about, what do I need to do to be an astro imager? What do I need to do? And frankly, I've never seen a real comprehensive list written by somebody who is an astro imager that agrees with me. By that I mean, we got a lot of people who have a heck of a lot of money and they'll buy anything. And we got some people who don't have a lot of money and they buy a lot of junk, and they shouldn't. And I thought it might be nice for me to tell people what they need to do to be an astro imager. Okay, so here it goes. Now, this is not a technical approach to astro imaging. I'm not going to tell you how to do astro imaging. I'm just going to tell you about what it takes to be an astro imager. If I can see the keyboard well enough. Okay. It didn't happen. Let me see. Here we go. Our overall presentation will take a certain approach. It's not the only way to take images, but we will cover many things a person new to deep space imaging needs to know. We'll omit a lot and we're going to exaggerate a lot, but we will be moving quickly. And there will be at times information on the slide up there that I don't talk about. If I don't talk about a particular brand or book title, or you can check out the slide and maybe Google it yourself. There's just not enough time to tell you about everything there is to tell you about. Just to tell you what's happening in the next hour, you should know that this is definitely a show for those who are not yet deeply into it. And I know some of you are deeply into it because I've seen you at GMARS and wipe that little grin off your face, Missy. I know who you are. Okay. And for those who aren't yet into it and they're finding it a little slow, maybe, this might clarify some things for you. Also, we're going to be talking about deep space imaging. Why is that important? And I'll tell you about why it's important. We must all judge what we need personally and how much we can afford according to our upbringings and life experiences and our financial means. I was raised in a big family that was always fed and housed, but because I had parents who lived through the Depression, we never spent money. What money there was put away for a rainy day. Occasionally, I got something new, but much of what I wore was already worn by somebody before I got to wear it. To this day, people tease me about my miserliness, my old equipment, and my general approach to spending. I'm cheap. My backyard observatory has a Celestron G11 mount. It's a Celestron and not a Losmondi G11. It's that old. In the late 1900s, last century, Celestron was getting its mounts made by that upstart company, Losmondi. I had bought it used and have been using it for more than 20 years. I hang around astroimagers and read Cloudy Nights and know people who replace their 2-year-old premium mounts just because Software Bisque has introduced a new Paramount. I once heard a guy say, it's only about 12,000 bucks. I personally don't see how only can ever be used to describe 12,000 bucks, but there are people in the hobby that do that. I have learned, however, that money properly applied to astroimaging equipment may have a value. That value of spending more money on equipment is that you can possibly get better results. You see, I also have a desert observatory where I do a lot of where I have a premium astrophysics 1200 mount. By the way, you'll be able to see it next week if you come on up, or not in a couple of weeks at the Star Party. Now, I never have to think about its tracking or how much weight I can put on it. I can take 5-minute exposures pretty much without guiding. Notice, though, that it is a 1200. That's an outdated mount for that. And I'm always getting asked by the people at Astrophysics who made it to update it with new encoders and new software and all this other stuff. But I just don't see the value of adding that equipment and its expense. That guy who can use the phrase only 12,000 would consider the upgrade a necessity, a must-have, and he wouldn't even think twice. We must judge what we need by our own standards. Money and the upgrade and performance you can buy with it can get you a better use of things, a better use of your time, and better quality images faster. It can eliminate frustration and reward you for your efforts. But sometimes the amount of money it takes just does not relieve all that much frustration. It doesn't save you all that much time or improve the results all that much. So you are better off spending it somewhere else. On the other hand, the lack of money can stop you from even beginning your astroimaging adventure. But if you're willing to put up with a few frustrations and not quite reach the level of performance you want, you can get along fine in astroimaging with relatively little financial bite. We each have to make our own decisions and all of that. And just know that I am coming from being raised by Depression-era survivors. And much of my advice will be along the lines of getting value for your money and getting started with stuff that will serve you for a long, long time. And the presentation is about the mainstream of astroimaging. That is why I am not including a discussion of C-star, dwarf, and other smart telescopes. You can get an astrophoto rig for as little as about $500 that can do all the stuff you need to do except the processing. And it's getting close to the point where it will do the processing. And we don't ask you to equip yourself for taking star trails with a good tripod and mirrorless camera, or any of the many things that people talk about as an introduction or an experiment in deep space astroimaging to see if you like doing it. We're not going to talk about that stuff. We're not talking about introducing you to deep space photography. We're talking about actually doing it. These things are all wonderful products, and they all have their place and they're fun to do. But while they may seem like an easy introduction to astrophotography, don't fall for it. They can also delay you unnecessarily as you spend money on what I call experiments. If you want to do mainstream astroimaging, you will eventually need more than all that. You'll eventually need mainstream astroimaging stuff. If money is an issue, don't go spending $500 on a smart telescope, which is an interim solution, an introduction. Save that money and add to it when you get more money, and buy what you really need for the long-term mainstream. Now, there is no use hanging around for the hour I'll be rambling if you are not willing to accept the ultimate challenge in astroimaging: money. It could cost you a minimum of a couple of $1,000s, and you might expect something like as much as $5,000 and that is for beginning astroimaging. Advanced imaging can easily be twice that for just the mount drive alone. Realize that you probably have already spent much of this money, though. You already have some of this stuff already. You probably already have an old laptop sitting around. So turning it into a productive astroimaging rig will probably not cost you all that $5,000. Where'd my cursor go? Cursor. But if you are starting from scratch, had no friends to borrow from, and you want the minimum usable quality, and you purchased it all new, where am I? Oh, I don't want that either. Boink, there we go. I got control of it again. But if you are starting from scratch, you don't have any friends to borrow from, and you want the minimum usable quality, and you purchased it all new, you're going to spend about $5,100 to become an astroimager. If you could put a dollar value to the time and patience, then it would be a whole lot more than that. Earlier, I said there were different kinds of astroimaging and that we were only going to be talking about deep space. Let's make sure we understand what I mean here. I've divided astroimaging into 5 types. There are also some subcategories: comets, meteors, showers, aurora, perhaps star trails, but they're generally a subtype or a mixture of these 5 major categories. Nightscape is the first of them. This is a nightscape picture, a picture of the Milky Way or other parts of the sky, and sometimes they're combined with landscapes. If you're interested in this kind of work, TAIC, the program I told you about, the Astroimaging Channel, has shows on the subject. Cheryl Wilcox from the Riverside Astronomical Society did a show on this stuff on January 6th, and you can probably do it with what you've got already at home. Electronic Assisted Astronomy, EAA, is using a camera to capture what the eye would normally see at an eyepiece, projecting it live to a monitor and watching it in much more detail and color than they can see alone with the eye. There is a lot more to it than that, and it is quite popular for outreaches where crowds of people can see what the telescope is seeing. Planetary, lunar, and solar imaging makes pictures of solar system objects. These objects have plentiful light, they're bright, and they're so easy to capture in videos. And then the separate frames are processed to bring out the most important details. We had another show on this on the Astroimaging Channel not too long ago, but that's not all we're going to be talking about. Scientific imaging, another type of astroimaging that we're not going to be talking much about, captures images of various objects to precisely measure their positions brightnesses, and colors. The filters, telescope, and software are specialized to discover information important to astronomers pursuing motion, the nature, and the composition of heavenly bodies. While most of the other astroimagers are getting pretty pictures, scientific imagers want to make nice, clean graphs and tables, like this thing here. A few years ago on the Astroimaging channel, Rod Palmier explained how he used amateur equipment to replicate the distance to M31 using scientific astroimaging. And finally, we get to the subject of our presentation, deep space. As I said earlier, these are the capturing of galaxies, objects in the Milky Way, nebulae. We look at the glowing gas clouds and the clusters of stars and the Messier objects and all that. We want pretty pictures. That's what we're after. So why did we need to distinguish between all these types of astroimaging? Well, each subcategory requires different set of equipment, software, and techniques. So you kind of have to decide what kind of imaging you're going to be doing before you go to it. ESA and planetary, lunar, and solar tend to use video cameras, taking hundreds or thousands of frames. They can get by with some inexpensive mounts, generally as long as they kind of track the stars. Even though they don't have to be perfectly tracking the stars, they'll still get a good image. EAA can be used at different focal lengths, both in planetary, solar, lunar, and they generally use longer focal lengths and generally have a crowd of people around watching it happen. Deep space, however, the kind we're talking about, uses cooled astro cameras. They're actually refrigerated that take long timed exposures. The focal length of the telescope depends on the target. Most importantly, the mount must be extremely well behaved, follow the stars precisely, and perhaps aided by a guide camera that corrects any imperfections in the mount. In short, different types of astroimaging take different equipment. And if you're going to start buying stuff, you better figure out what kind of pictures you want to take before you start buying it. Now, this different equipment is used in different ways, of course. A session of EAA, or electronic assisted astronomy, for any given object may simply require pointing the telescope to the target, starting the software and the video, focusing, and watching the image developed on the monitor. You can be in daylight, or if you're doing a daytime object like the sun, or a well-lit tent with the telescope outside in the dark, showing the result on a big screen with a high definition television. The results are available in near real time. You can watch it happening. A target may be imaged in as little as 15 minutes. Nightscapes are different. They're often taken on a hike with a particularly beautiful part of the Earth, with a good DSLR or mirrorless camera and a wide field camera lens. They don't use a telescope. Tracking is not required. Most of the controls you need for getting the image are available right there on your camera. An image can be a single image taken in as little as 15 seconds. Deep sky targets, however, are generally invisible to the naked eye because they're so dim and so far away. They must be captured over hours at a time. The camera should be artificially cooled to reduce noise. A session can last most of the night, and one target will contain dozens to hundreds of exposures, each a minute long to 5 minutes long. Now, some kind of computer to capture all these images is almost always a necessity in deep space imaging. Again, all these different types bring out different data in different ways. In theory, there are similarities to the processing. Individual frames must be aligned and generally calibrated, registered so that the stars and other details all align, and then stacked together one on top of the other. Oh, and that throws out all the bad pixels and the imperfections that you might otherwise get. They're caused by defects in the cameras and just random weirdnesses that go on. They go on all the time. Then the colors are emphasized or de-emphasized as needed. Things are sharpened, noise is removed, and the image is finally displayed. But depending on how the image was captured, the processing may be substantially different. EAA will align each image as it comes down from the camera, sometimes in a video format, building a brighter and crisper image with each new downloaded frame. And you can see it building, getting sharper, cleaner, and brighter all the way along. The processing will be in the first place in real time, done by adjusting sliders in the software as you watch. And these sliders perform statistical tricks with the information, and it gets prettier in each new frame that's added. You can save the image and later go back and process it further if you like, but the goal is to capture it and display it right there on the television, right while people are watching. Deep Sky, however, takes its time to do all those steps at home afterwards, and you'll spend as much time processing the picture as you did grabbing the data while looking at the stars. It's not in a hurry at all, and it uses a pretty much different set of software. So, can equipment from one type of astronomy cross over into space imaging? Well, yeah, maybe, but you're buying yourself a whole lot of trouble. So you should really think about getting the equipment right in the first place. There's no such thing as a perfect scope, mount, camera, sensor, or any piece of equipment for every type of astrophotography. But you should get started with something. Start with what you have and get moving. Having said go with what you got, remember that this presentation is about doing it the right way. If you are starting from relatively nothing, it's not about adopting or adapting other pieces of equipment and techniques in order to do it some cute way. What are the demands of deep space imaging that drive the equipment choices? It demands a lot of light from a relatively dim object. Maybe a half dozen deep space targets are visible to the naked eye in dark skies. Most nebula, for instance, require a telescope and an exposure of more than a few seconds just to see. By the time the photons arrive at our eyes, they're all a bit jumbled by the atmosphere. The electronic noise in our camera and all around us in our environment are carried by photons, and they can skew the count of photons and the light coming into from the distant target. One way to overcome these issues is to cool the camera. Remember I said the cameras were refrigerated? You cool it to get rid of the noise. And another way is statistics. You average things out. You just don't accept them as they come out of the camera. And to get a good solid number for averaging, we need a big sample size. So in the case of astroimaging, that means lots of time to collect the exposure, lots of seemingly identical long exposures that are going to be averaged together. And our targets are not just holding still. The Earth turns one whole rotation in a day. To our eyes, the targets seem to move pretty evenly across the sky, but that's not exactly true because of the atmosphere itself, for instance, acts as a large lens. And stars travel at a slightly different rate depending on where they are in the sky. If the stars were moving at a smooth rate across the heavens, we'd need equipment that can follow these targets very, very smoothly. The gears must be polished, smooth, perfectly circular. The motors must be constant as they push. The parts must fit together well, so there's no slop or slippage. But there are other things that get in the way of perfect motion. You can follow a star, if you can center your mount's motion, it's precisely the same as the Earth's pole. But if you are not pointing the main axis, let me see how this works here. Oh, I'm going to get that to that in a minute. If you're not pointing at exactly the right, if you're not rotating around the right point, things will get messed up and your stars will drift around. If your motor runs low on power or gets a power surge, it's going to run too slow or too fast. If you have too much weight on a mount, not only will it move more slowly, but it could have all sorts of problems. So I could go on and on about tripods sinking into the ground or an alligator tail whacking the bottom of your tripod, or maybe you bumping it up with your head, which I've done. But fact is, all this is not to scare you. It's just to tell you that in addition to having a very good, well-made mount, you might need a guider. Few machines are made to such critical tolerances that they can cope with all the vicissitudes of a night of image. So you get yourself a guider that includes software. Can you see that? No, you can't see that. You get another piece of software. You get another camera sitting up here. You still can't see it, can you? There it is. There's another camera sitting up here on a little baby telescope above the big telescope. It's constantly taking pictures, maybe 3 seconds long, and it analyzes the stars for where they are in the field. And then it takes another one and it analyzes the stars. If the stars have moved, it sends signals down this wire to the mount and tells the mount to move, so that if the mount is not moving properly and following the stars precisely, it'll be told to correct it and get back to where it belongs. So you need a guiding system. And let's return for a second to the different types of astroimaging. The demands of long exposures and all that it carries with it is what really distinguishes this equipment and techniques that separate deep space imager from all the other types of imaging. Deep space, generally speaking, and scientific to a limited degree, put the greatest demand on long exposures, and long exposures put the greatest demand on your equipment, particularly your mount and your guiding system. If you bought equipment for other things, it probably is not going to be up to the task. That's why the most critical element of deep space imaging is a good mount. You spend your time and money getting a good mount primarily first. That's the most important thing. It should be an equatorial mount so that it's got an axis that points just to the north, exactly precisely to the north, and it moves around that axis. And you have to align that axis to the north every time you set up. It's one of the important things. Avoid scopes that move only in altitude or azimuth. These are some very good mounts, very, very usable equipment, but you need it to rotate in the equatorial mode. That means so that it follows the stars as they go across. Many visual mounts are in fact alt azimuth, which they can change altitude and they can change azimuth, but they can't follow the stars in the big curve. Don't go there if you're into deep space imaging. Secondly, get enough mount to carry whatever you plan to put on it. This counts the telescope and a camera, of course, but you'll also have the guide camera, additional optics, maybe a small computer up there, and perhaps a few other things. And there is no standard for mount capacity. Capacity is usually stated in weight, but the length and width may be just as important to consider. A long, lightweight refractor may overload the same mount that handles a short, heavier SCT quite easily. Generally speaking, you should look for a mount that is rated to hold twice the amount that you will have up there. And always consider the mount's periodic error. Pretty much all mounts have a regular errors that pop up in regular time bases. That's because everything's round and sometimes they aren't perfectly round. Okay, so you have to be able to adjust for them. Get something that has a good periodic error rating in the first place, and to add to it software that allows you to correct whatever periodic error is. That is, when your mount is about to slow down, it actually kicks in extra energy so that it goes faster and eventually straightens it out overall. That's something else you're going to need. Now, there's a new type of drive system called harmonic drives. I haven't decided much about them. I think I'm not going to go into depth on it, but you might want to consider that at some point. Tripods, you need a good, solid tripod, something to hold that mount down. So you're going to have to spend some money on that. And you need some direct computer connections, some USB ports, And this usually is coming from your computer. It tells the mount where to move, how to move. And remember when I said that guiding thing where it recorrects every 4 seconds or so? That's also one of those plugs in there. So you're gonna have to think about that when you buy it. Anyway, the mount's the most important thing, so get a good one. To the telescope, almost any telescope will work fine for you, but I would strongly suggest that you get a refractor. That's one with a big lens up here, a focuser back here, and then back in the back is where you would put your camera. Okay, there are lots of other kinds of rigs, but you know, Newtonians and Swiss Cassegrains and Ritchie Chrétiens. But honest, you really want a nice simple refractor, and you want one about 450 to 750 or to 700 millimeter focal length. It's a nice medium size. Get it at least 70 millimeters in aperture. This is the aperture. This is the focal length. Okay. You want a good, strong focuser, and you want it to be apochromatic. Apochromatic means that it brings all of the colors to focus at the same place. If you don't get an apochromatic, you'll have stars with little green edges or blue edges, or blue or red edges is what you'd actually have. Green pretty much stays in the middle like it's supposed to. A refractor is good because it's small, tough, and easy to handle. Next thing you need is a camera. If you have a DSLR, you're ready to start right now, or a mirrorless camera. You're ready to slap that sucker on the back of the tube and get to work. Okay. But if you really want to get into it, you're going to have to get something with the cool sensor found in dedicated Astro cameras. So go ahead and, you know, there's lots of choices for this. And by the way, I'm not an equipment freak. I don't know those things. Some of the questions you'll be asked is, should it be a one-shot color camera or a monochrome camera? One-shot color cameras take their pictures through a set of interior filters permanently attached to the sensor. And that's how they get their color. Monochrome cameras, however, have a filter wheel, and by shooting through the different colored filters, you get the colors from that particular picture. One-shot color is easier to work with and is quite good for most things. For the first few years, you won't be able to take pictures, and you won't be able to notice much difference. However, as you get better, the top end is in LRGB imaging with narrowband filters and stuff like that. So it's not that hard to take pictures with LRGB, which is this monochrome stuff over here. So I would suggest you might, you go ahead. If you know you're going to take this for seriously, get the monochrome type camera. Otherwise, you're fine getting with the one-shot color camera. You may have heard the term CCD and CMOS and wonder how it affects you as a beginner. It doesn't. You can't buy a new CCD camera anymore. Everything's been replaced by CMOS. And so just keep that in mind if you are going to get into this. Sensor size is your next choice, and this does matter. Sensors come in all different sizes. One of the most popular is this APS-C, which, as you can see, is about this big, and full frame is this big here. That's the same size as your 35 millimeter camera. By the way, this is all available on YouTube if you would like to. I see you taking pictures up there trying to catch all this stuff. You can also go through it on YouTube at the Astroimager channel. I'll tell you how a bit later, okay? So it's already been recorded. So you can just sit back and relax, watch the show if you want.
It will also be on the PVAA YouTube channel.
And it'll also be on the PVAA YouTube channel, of course. Okay. I need to backtrack a little bit here. I've so far made 3 fairly solid recommendations that you should have in your head. One is get the best mount you can afford. That's number one. It'll always be number one. 2 other combinations or 2 other recommendations kind of work together. I said a 450 to 700 millimeter focal length scope and a sensor of at least APS-C that size there, I think that size there, or bigger. These two work together because focal length and sensor size determines your field of view, how much your camera is going to capture. And you want your field of view to match your targets. Of course, at the beginning, you're going to have lots of targets. This is space, this picture right in through here. That's what space looks like. Kind of a poopy picture, but you know, forgive me, it was hard to get this done in the first place. Anyway, where are we? Come on, cursor, show up. There you are, friendly little cursor. So that's space. That's what it looks like. This is space as your color camera would see it in a 540 millimeter focal length. If it were a 1200 millimeter telescope, you would see less of it, but it would all be bigger. If you had a full frame sensor, right? Oh, you can see the cursor now. If you had a full frame sensor, it would be this much of space that you could see. If you had an APS-C sensor, this is how much you could see. Okay, so that's space and it stays the same. This is in a full frame sensor, it stays the same. And this is in a APS-C sensor. You'll notice that the size of the horsey, the size of the horse head has not changed. You can see from here to here in this sensor. You can see from here to here in that sensor. The same chunk of space, but you see less of it at the same size, incidentally. And this one here is to show you that what you usually find out is like this is the one taken with the full frame sensor, and this one over here went too far. This one over here is okay. Go back one. Turn that on. This one over here is what you would see in the full size sensor. This is not what you actually see in the APS-C size sensor. What you've done here is you usually blow it up so it looks bigger. But you will notice if you had good resolution and everything here, that you can actually see the same amount of detail in this, the same number of stars, the same everything else like that. This is just blown up. And when you blow up a picture, it all gets a little bit fuzzier. We touched on auto guiding a little back. It's necessary at some point to make up for the problems in mount speed and other gremlins. So you need to either add an off-axis guider or a separate telescope with a camera on it to take those pictures. And you need a solid connection between all of this stuff, because if this is wiggling or that's wiggling in relation to each other, you're going to have a problem. That's one of the things you need if you want to be an astroimager. You can do some limited astroimaging without a computer if you use a DSLR or mirrorless camera and you do not guide. But this is a presentation about how the beginner can do imaging well. And that will take a computer to run the session and to store the results. It does not take much of a computer to get all this stuff done. A simple Windows 10 laptop, beaten, scratched up, will do fine. Get one with at least 4 USB parts, at least one of them USB 3 if you can, and you should be good to go. Many people have found that happiness with a mini computer can cost as little as $129 and can do everything you want it to do. So it's really not all that complicated for the computer part. How simple can the computer be? I don't know. Back about 2018, people were writing code for Raspberry Pis that could handle the complete job of running an astro imaging session where you went out and took the pictures. ASI Air from ZWO is a Raspberry Pi. That's this computer up here, just a Raspberry Pi, which is like now about an $89 computer. And they packed their own software into it, so it'd be really cool. But a simple mini computer, a Windows 10 mini computer, will also do the same job. You can get away with it pretty easily. There's a lot of software you can use that's free, Nina in particular. and it'll run the whole session. The last category of stuff you need is junk. Stuff you've probably got already sitting around the house. You'll probably need a little baby table. You probably need some extension cords. You might need a 12-volt battery or a power supply or a long extension cord, something like this. I mean, this is pretty good. I would add a ground cover under here, just a big piece of carpet, and maybe a cooler for the beer, and it would be fine. It would last me all night. You got two kinds of software you got to buy. One is the acquisition software. I already talked about Nina. What it does is it gives you a choice of what you can image. You tell it what you want to image. It knows where it is in the sky. It connects to your computer and your mount, and it moves this telescope to where it belongs. It takes some pictures to check that it is where it's supposed to be. It focuses itself, and then it proceeds to take a bunch of pictures for you. Now, I kind of oversimplified that a little bit, but that is what it does. For this task, I recommend Sequence Generator Pro, which is a beautiful and very powerful program, very well controlled. Or Nina, which is also a very powerful program. But I got to tell you, SGP costs $150 to start and $60 a year to renew and keep it going up to date. Nina is free. So if you're listening to my recommendations, we're talking about Nina here. That's probably what you're going to want to get. Where are we? The other software you'll find necessary is something to process all the image. The real art of all this is processing the images. Okay? This is not a presentation about processing, but if you're asking me, I'm going to recommend you learn PixInsight as soon as you can. It's by far the most powerful astroimaging software. It's a little bit obtuse, a little bit strange looking, but if you start off slowly, ignore most of it, and just step through the simple things you really need, you can master it fairly easily. However, it costs a pretty penny, a little more than $300 as a one-time purchase with no later, and you don't have to repay every year. And to really get it to work magic, many people add add-on software for specialized jobs. And that can cost you $100 at a pop. So it's pretty expensive. There are, however, a number of inexpensive programs that you can buy that can do the processing for you. And if you go to the Astroimaging channel, you'll find several programs based on free software. Now, getting down to business, this is my one person's opinion about what you should have to start, or at least where you should be trying to get when you are really doing good deep space astroimaging. A mount that is rated to hold 30 to 40 pounds with low and correctable periodic error. A nice 450 to 700 millimeter focal length scope of 70 millimeters or aperture or better. An APS-C or larger sensor in a cooled camera, a guide system, a computer, Nina, and PixInsight or some other free processing software, and lots of support stuff to connect things, cables, and make yourself comfortable. Now, you've seen this before, and there are no surprises. You've also heard me say if you are willing to put up with a little compromise, you may already have good substitutes for some of these things. If your scope has too much focal length, for instance, like the ubiquitous 8-inch Schmidt-Cassegrain telescope from Celestron, you just have to be a lot more careful about mounting, aiming, and guiding it. And that will limit the targets that you can reasonably get. If you cannot afford a guider yet, you just have to be better at polar alignment, take shorter exposures, and use periodic correction in your mount very carefully. If you can't afford PixInsight, there are other alternatives. So you can get by, you can get started with less. This is about how to do it well, not just getting by. Now for some old geezer recommendations, because I am an old geezer. More expensive equipment can potentially get you better results. More importantly, it does things more easily, less frustrating. Less expensive equipment, However, usually works pretty well if you bought correctly. As has been said in response to the question, Nikon versus Canon, frequently asked in photography, it's not the camera, it's the person behind the camera that gets the great pictures. It's true that many of the equipment items, regardless of whose name is on the side of the piece of kit, all that stuff comes from the same factories. But that does not mean that they are the same product. One vendor may sell the telescope from that factory at a certain standard. He only accepts the top 10% of their effort. Others may accept the top 50% of their offer. So just because it's made in the same factory doesn't mean it's the same product. If you buy from Astrophysics or Software Bisque, Stellar View, it will be a very good copy of whatever item it is. If you buy from others, it may be, or it may not be the best example the vendor sells, even though it meets the company's published standard. And one other thing you notice about premium mounts, premium equipment, is that they just work. You don't have to think all that much about it. Everything in life is a compromise. So is astroimaging. You can save money, but there may well be a non-monetary cost to that. And value does not necessarily increase with price. If you plan to spend $1,000 on a mount, you will not be long-term happy. If you add an extra $1,000, spend $2,000, it will make a whole world worth of difference. If, however, you've already got a $5,000 mount and add an extra $1,000, you won't be a world happier. Maybe just a little baby asteroid of difference between $5,000 and $6,000 on a mount. Of course, that asteroid is not a whole world of difference, but it may be something that matters to you. Quit fussing it all and get something to take pictures with. Get started. Unless you hang around with the cool groups of buddies, everything in imaging has a cost. Some people experiment. They try something, see if it works or if it's good for an introduction, and then they can sell it later to recover the costs. I call this experimenting. It has its value, but it also has a deep cost. You simply can't sell the stuff for nearly as much as you bought it for and had it shipped to you and back to the next guy. You cannot try out equipment. There are 90-day trials on some of the software and stuff like that that allow you to try it out, but you just can't ship stuff around and really try it out. So make your decisions wisely, not just collecting stuff as you go and losing money every time you sell equipment. Don't waste money along the line. Much of the stuff you use for beginning astroimaging can be quite useful later on. Look, I am an environmentalist, but I don't want to sound like an environmental ad. When you've gotten that large 152 millimeter aprochromatic refractor for $9,000, a few years down the line, you will still find many uses for your 70 millimeter aperture, 500 focal length refractor that you bought to start with. The beginner stuff can become the central part of your solar setup or your EAA main scope or a pop-up kit for outreach or any one of a number of things. So buy quality now. And I've said it repeatedly throughout this presentation. Use what you have. You can learn a lot and make great pictures with that older DSLR that you already have. The 8-year-old laptop can run an imaging session pretty much the same as a brand new one. The important thing is to get going. Will you see the difference? No. Your eyes are not good enough to see the difference between a shot taken with the equipment I have described compared to the stuff you would dream about having. For the first 8 to 10 sessions, which may be a year, you'll be limited by your skills, not the equipment you bought. You should not even pretend to fuss about the RMS of your guiding or the size of your pixels. Fact is, even if after you've learned all the tricks of the hobby, the weather, light pollution, things you have no control over, not your equipment, those other things you have no control over will be the limiting factor in the images you take. If it's windy, bad seeing, mediocre transparency, the image you generally get will be no better than a $25,000 rig. You're great with your $5,000. The equipment I have described here will make great pictures for you for years. More expensive, more modern equipment will make it easier to take the pictures, and more repeatable perhaps, but with fewer glitches and surprises. But improvement comes through intelligent practice, not from upgrading equipment, at least for a while. Buy quality, budget and save, use what you have, borrow when you can, buy used, sell stuff, and join the crowd, guys. Get some friends that can sit around with you and help you with stuff. Watch the Astroimaging channel. There's a lot to learn, and you get a lot of it from interacting with other people. According to recent Google search for YouTube videos about astroimaging, there were 2,200,000 such videos out there online. You'll notice that the first hit, at least for my search, was the Astroimaging channel, which I watch every Sunday night. So join something like that. I mean, just all you got to do is watch it. They've been bringing presentations every Sunday afternoon for more than 10 years. And you can look them all up. They're still there. What is that? Oh, yeah. Here is a picture of a database that we've got, and for each of our programs, how it's described and all that other stuff. So it's, there's a lot of information out there. Warren Keller and who is this? Bracken. They've written some good books for it, and you can pick them up and read them. They're the importantest thing is an old expression. It's RTFM. RTFM, and it means read that fine manual. It means it's expressed in other ways in other contexts, but read the manual. You'll find out that there's a lot of stuff you need to know. So that's my advice to those who want to become deep sky astroimagers. Does anybody have any questions? Thank you. I'll get to your question, but I learned in coming tonight that either you really appreciate the fact that I do okay presentations when I come, because I've been here before and I got re-invited, or it's really hard to get a substitute speaker on a short notice. Yes, sir, your question.
That looked excellent, I mean, super excellent, that were taken from downtown Los Angeles.
Yes.
Am I right in saying that with modern technology, with modern astroimaging, that the place where you take astro images is pretty much secondary?
No. It's very important. It's very important. The image that you see taken, a quality image taken from downtown, it took perhaps dozens and dozens of hours of taking the image. And you need to do that to separate the light coming from the outer space from the light coming from the haze around you. You can subtract it out if you do it, but only if you have lots and lots and lots and lots of data. That same data taken out in what we call a Bortle 1, or like in GMARS Bortle 2, 2.5, and that's how dark it is compared. You could have gotten in 20 minutes, half an hour, and that counts. Okay. Yes, you can take some really nice pictures from downtown. Glenn Diekman, who's a orthopedist someplace over at Kaiser, I think, is one of our crew, and he takes wonderful pictures from his backyard in Rancho Cucamonga. I take some really nice pictures from my backyard in Moreno Valley, and I can do that if I want to spend a lot of time on it, or if I want to use special filters and get very limited color out of it. And anyway, but it's very hard to do. It does matter.
And you could spend as much on the filters as you like.
Yeah, it just, it just, yeah, it doesn't matter. Yes, other questions.
Have any favorite targets that you want to go to?
Well, like anybody else, I think the Messier objects are the greatest hits. For those of you not familiar with the Messier object, a comet hunter back in the 1700s found big blobs of some kind or another. And he was happy because he thought they were comets, and comet hunting made you rich back then and favored of the king. Only he noticed that they didn't move. Comets move through the sky. That's what makes them comets instead of gas clouds. So he made a list of 100 and, well, he and his buddies made a list of 110 really cool things to look at up in the sky. They didn't know what they were, but that's what and those are the greatest hits. Okay. Obviously the Horsey, which isn't on that list, incidentally, but the Orion Nebula is right next to it. I mean, that's going to be up there. So double cluster is not on the list, but it would be up there. So that's I think the main ones. And you've got astronomers here that can tell you other ones, but you got to go through the Messier list. Some of them you don't have to go through, but there's at least 60 or 80 that are good to look at. Are there other questions? Thanks for, yes.
Tell people how to find the massive GMR
Can what?
to your location for astronomy next week.
Oh, your club is coming out to the, your club was an original sponsor of GMARS years ago, hundreds of years ago, back when we were in junior high. Remember, Ron? And yeah, so you're coming out to GMARS for the star party out there. And when you come out, yeah, you can take pictures out there, great pictures.
To get to it, you have it on your website, don't you?
Yes. Yeah, we have directions on our website, and I imagine that your club would provide directions because there'll be, pardon?
How to get there.
Oh, okay.
You can find it on your website, and I think. our
Just a
website.
second.
There'll be directions there somewhere.
Usually when I type those first few letters in, it already fills rivastro.org. This is our website. And this is GMARS.
Hang on, you're not in the,
Pardon?
it's on your screen, but not.
I don't know how to do
Okay.
things. I thought I was still sharing my screen. Maybe I'm sharing the wrong screen.
Just move this to the second screen over here.
There we go. I fixed it. I didn't fix it.
And
Someplace around here, there's directions. Here.
yeah.
Okay.
We go to directions. So first of all, see, he went to rivastro.org. Okay. And so, but if you just type in like Google Riverside Astronomical Society or even RAS kind of thing, it should get you this page. And here's here's where it's at. Okay, but you just Google map it. And we can
The nearest hotel is right. No, it really, I mean, right, it was right there, but it's like getting shrunk.
Yeah, I don't say.
No, the nearest hotel is about 300 feet away, maybe 800 feet. It consists of a set of Airstream trailers. There's about 8 Airstream trailers. Well, who was it? The B-52s or the B-52s, which were the rock band. They own it.
Really?
see, there's the 10, right?
So we're gonna have music when we go? Never heard of
No, no, it's a bed and breakfast. Hey, my sister and her daughter and her new husband will be here. I mean, my new husband, I mean, they just got married on December 31st. They've been going together for like 40 years, but they decided to get married. I don't know. When you come out there, there's a little bunch of fun things to do. The Integratron, did you see it there? That the Integratron is it's a dome, big dome, and you can go in there and get a sound bath, and the spirits will, and then giant rocks way up there, and it's a giant freaking rock. I mean, it's like huge rock. Giant rock. See that giant rock? And oh, you got to see the orchids too. It's April now. There's a place that grows orchids right across the street.
how.
Anyway, there's G Mars. The easiest way to get there is to come down to where the post office is, which is right here, and turn left, and then go to the sign that says G Mars and turn right.
All those potholes, right?
There are no potholes. There are no potholes in our roads. It's all sandy road. And by the way, it's all free. Of course, it's free. It's too much work to collect money.
Well, that's why.
Hey, we have a really good time out there, you know.